Okay, it's time to start. So you saw that I already copied the theorem we ended with last time on the board again, because I actually want to start by proving this theorem now, so that you actually know why the degree of such a map of balanced fans is actually constant. And also just so that you keep in mind where we are going in a sense, the situation we want to use this theorem in just a bit is where this is the moduli space of tropical stable maps. F is an evaluation morphism. This is just R2 to the something, which of course is irreducible. And then we want to show that the degree of the evaluation map is constant using this. And we have, of course, then some multiplicities with which we count our inverse images of a point. Yeah? So a point here in R to the n, it's actually a tuple of points, right? R2 to the something. It's a tuple of points in R2. And the inverse images under the evaluation map are exactly those tropical stable maps that meet those points with their marked points. So roughly you can just think the tropical plane curves that pass through those points, right? And each such tropical plane curve has to be counted with a certain multiplicity to make the statement true that the degree of the evaluation map is constant. And I also need to show you, of course, that this multiplicity, which appears here, roughly just, some lattice index, equals the multiplicities we've been talking about earlier when we've been counting tropical curves. And once we know that, you know something that I promised rather early, that it does not depend on where you pick your points. If you count tropical plane curves passing through those points with the right multiplicity, you will always get the same number. Yeah, this will be a conclusion of this theorem once we proved it and once we convince ourselves that the multiplicities are what they should be. Okay, so let's prove this. And in a sense, we have prepared the proof last time, so there's not very much left to be done here. What we do is we take our fan sigma 1 and push it forward with sigma 2. Now, sigma 2 is irreducible, and this is a fan of the same dimension, so it must be just a multiple of sigma 2, since sigma 2 is irreducible. It must be just a multiple. That's something we showed last time. Two fans of the same dimension, where with the support of one contained in the support of the other, and this other is being irreducible, then they must be equal up to a constant, right? Now, okay, when I say equal, keep in mind the fan structure, the concrete fan structure, is something that I actually never really care about, right? I can always go and subdivide my cones to make things work, and then I'm happy. And so I can always assume that these and these have the same cones. And then it's really just the weights that differ by a constant factor. Have the same cones. And this is a statement that holds without restriction in the sense that I can just go and subdivide if it's not already true, right? And subdividing doesn't hurt me. Okay, then the subset, these walls, somehow the locus that I should avoid when I try to make my degree computation, I can just define to be the support of the codimension 1 skeleton. Of the push-forward fan. And once I do this, 1 and 2 are automatically satisfied, because then I'll be in the relative, if I be in the relative interior of a cone that is, if I avoid these walls, by definition, I'm in the relative interior of a top-dimensional cone. And also, all the pre-images will be in the relative interior of top-dimensional cones, because the lower dimensional cones are being mapped to lower dimensional cones, because I guaranteed that they have the same cone structure, right? So then 1 and 2 hold. But 1 and 2 are not so exciting, right? What we are really excited about here in this theorem is the third part. That is the nice thing. So let's talk about this. So for any choice of Q, as in 1, there's a bijection between inverse images of Q, points in the inverse image, and inverse images of the cone, so to say, and sigma in sigma 1, which are top dimensional, that are mapped to the cone of Q. Yeah, this is my notation for the cone of Q, the cone around Q, right? And every cone that maps to this guy will have a point that also maps to Q, right? It can have, we cannot have more than one point in a single cone because this map is a linear map. And it's also, when restricted to a cone, a linear map. And yeah, linear maps between spaces of the same dimension, it's injective, it can have at most one pre-image, of course. And since this cone does map to this cone, it will have precisely one pre-image. Okay, so that means I can write my sum over all P that get mapped to Q, and then this multiplicity, PF. I can write this as a sum over all cones sigma that are mapped to my cone sigma Q prime. And then it's, and in fact, let me erase the Q. Let me just call this sigma prime to sort of, get rid of the Q, because it only depends on the cone that lives around Q and not on the special point that I picked inside this cone. Okay, and then I can write the weight of sigma 1 of sigma divided by the weight of sigma 2 of sigma prime times this lattice index, which is span sigma prime intersected the lattice modulo the image lattice, f of span sigma intersected their lattice. Okay, now let's have a look at this. Oh no, maybe, okay, let me use different color, it'll be nicer, better to see. Okay, now I want you to look at this and tell me whether you saw this expression before. The sum over all sigma that map to a certain cone in my image fan, the weight of these cones, the lattice. That's exactly by definition the weight of the push forward of sigma 1 of sigma prime, right? If you don't remember, please look back in the notes. Then you should see it. Yeah, but that's nice because that means, so this is just, this whole thing is just the weight of the push forward of sigma 1 of sigma prime divided by the weight of sigma 2 of sigma prime. Aha, nice. But what is this? Remember those two fans, the push forward of sigma 1 and sigma 2, they only differ by a factor. Yeah? So their weights only differ by a factor. So the weight of one guy divided by the weight of the other guy is precisely my lambda. Okay, and lambda does not depend on the choice of Q. This argument does not depend, this equality does not depend on where exactly my Q lived, right? Because this is always going to be the weight of my push forward fan. So that's already the proof, and the reason why it went so fast today is of course that we set up all the preparations already last time. Okay. Yeah, one notation that I hope is going to be helpful is the points. If we have such a situation, then we say points in sigma, or in support of sigma 2 minus the nasty subset, minus the sigma to 0, are called in general position with respect to this map F. And if you have points in general position, then you know that their fiber is finite, and every point in the fiber is contained in the interior of top dimensional cones. For a point in general position, the fiber is finite. And every pre-image lives in the relative interior of a top-dimensional cone. Okay, that's nice. Okay, now what if sigma 1 and sigma 2 are marked fans? Which is a situation we like already because our tropical moduli space is going to be a marked fan. Let me call V1 up to Vn the markings on the rays of some cone, of some pre-image cones, sigma p and sigma 1. And let me call W1 up to Wn the markings on the rays of the image cone, sigma q prime in sigma 2. And then I claim that the multiplicity, mul pf, which actually only depends on the cones, so you could also call it mul sigma f, anyway, mul pf, is the absolute value of the determinant of the matrix of f expressed in those bases. V1 up to Vn and W1 up to Wn. Why is that the case? Why is that the case? Since this lattice index, the span of sigma q prime intersected set to the S modulo the image lattice f of sigma p intersected set to the R. This index is going to be the determinant of the matrix of f with respect to a lattice basis, right? So if I pick a lattice basis of this thing, map it forward with f, then I get a square matrix if I express the images in a basis of this thing, right? And the determinant of this square matrix is precisely the index of this lattice here. So equals the determinant of f with respect to a lattice basis. But now here we didn't take lattice bases. We took those marked rays, which do not generate the lattice, but we can base change from those to a lattice basis. And base change from V1 up to Vn, respectively W1 up to Wn, to a lattice basis, what does it give us? Well, it gives us as factors precisely the index of the lattice spanned by those guys, right? Respectively, on the other side, 1 over the index of the lattice spanned by those guys. And what is the index spanned by those guys? Remember, these are the markings of our marked fan. And remember how we defined the weights for a marked fan. The weights were precisely given as the lattice index of the markings, right? So gives us factors. So we get for this space change a factor which is the weight of sigma 1 of sigma p, respectively for the reverse space change on the other side, 1 over the weight in sigma 2 of sigma q prime. Okay, and now we look at this. This is the multiplicity, this thing here. Yeah, here it's written nicer maybe. This is the multiplicity. This lattice index is equal to the determinant of f with respect to lattice spaces. And these two factors are given from base changing from lattice spaces to our marked vectors. And so we can express this whole multiplicity just as the determinant of a matrix F expressed in our markings. Okay, why is this great? Because this tells us that this multiplicity we're talking about is really the multiplicity I promised you earlier. Why is that the case? Remember, if we have some tropical curve with some length here, yeah? Remember that we wrote this as L1 times this guy plus L2 times this guy, right? Where we shrink one of the edges. Maybe I should write down some markings to really make this pictures precise. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And those guys here are precisely the markings of our rays, right? And then those big matrices we set up in the sometime last week, I don't quite remember, those things where we had like a root vertex position for R2, for the R2 coordinate, right? And then we had L1, L2, L3, right? These are precisely in those coordinates, right? So with this big matrix that I wrote down last week, I did give you the evaluation map in the basis given by the markings of my rays, right? So that's what I did. So that big determinant that I computed was nothing but this lattice index times weight guy that we used here to define the multiplicity more generally for a map of fans. Yeah? So this tells us that what we denoted as the multiplicity of gamma xih for some tropical stable map is actually equal to the multiplicity of this element viewed as a point in the moduli space of the map if, where f is now a map of fans and this is just a point in one of my fans. Yeah? This is the equality that was missing to sort of make this to make this bridge, to connect this to what we've been talking about before. There's one more ingredient missing. So far, we discussed the evaluation map as something that is linear on each cone. This is how we viewed the evaluation map, sort of, as this matrix, something that, of course, is linear on each cone. But in this theorem, I ask for a map of fans. I want a map which is globally linear. Right? So what I still need to show you, or to tell you, don't want to really go into the computation here, but what I still need to tell you is that after we took this M0 n drop and embedded it into this large vector space R to the n choose 2 minus n, the evaluation map is really something that is globally linear on the surrounding vector space and just restricts to precisely what we discussed before on our cones.
But for a big giant matrix, is there any significance to like eigenvalues of that matrix, or just any invariance really, or is it just by construction? It gives us what we want.
By construction, certainly yes. This is what we want. I never asked myself what the eigenvalues of this matrix are and whether they tell me anything. Okay. So, sorry. Yeah. Anyway, so here's a lemma that says the ith evaluation map, which is sort of just one component of our big evaluation of n points later, yeah? The ith evaluation map, which goes from the tropical stable map space R2 some degree delta, which I want to identify, of course, with R2 times M0 little n plus number of elements in delta, trop. Sorry, now I need to, this is, okay, slight abuse of notation, right? It's just this target space for my map, and the map goes to R2, yeah? And this is linear. It's globally linear. Yeah. Why that? Well, let's talk about EV1. How do I need to give you an element inside here, right? An element which is gamma xih inside here in coordinates, yeah? In coordinates, I need to give you a root vertex and all kind of distances. Root vertex for my R2, right? Which I identified with EV1 of, just h of x1. Let's put it like this. EV1 of the whole thing, or h of x1. And these are the distances. Distances between ends, because this is how we embedded our tropical curves into the r to the n choose 2 minus n, right? So those are the coordinates I want to use for such a guy. And so, you know, if I take EVI of B, EV1 of B and AIJ, what's the image going to be? I just evaluate the first point. What is the first point? B. It's just B. So it's just a projection. Good. We all know that projections are linear maps. No worries here, right? What about at the other EVIs? For I is not equal to 1, then EVI of B AIJ just going to be B plus 1/2 times the sum over all ends, which are not the ith end and not the first, k from 2 to number of ends, which is little n plus elements in delta, the distance of 1 to k minus the distance of I to k times vk, where vk is, of course, in delta, yeah, delta. Let me put it differently. Vk is 0 if k is a marked end, because marked ends are contracted. Marked ends we view as the marked points, right? Marked points. Those guys that get contracted to just a point, yeah? Then vk is 0, of course. It's vk here. And else delta contains some vk's, right? Sorry. I hope you understand what I mean, yeah? K from n plus 1 to number of elements in delta. Yeah, these are the directions. This is my degree. Yeah, so you can think this, right? If we are in degree D in P2, which we're going to be in just a bit. Yeah. So these are my prescribed end directions, which are prescribed by the degree. Let me put it like this: the VK are the prescribed end directions. Prescribed by degree. Delta is just a multiset of directions, right? A multiset of directions of ends. Yeah, okay, and this is honestly just a computation, so I don't want to prove this now. We can just... There's a question? Yes, please?
So you don't care about the fund structure on F2 because you are interested in the degree of...
Well, you know, in a sense, after the theorem, I will do an example, okay? You'll see a picture. But I have to care a little bit in the sense that I want to understand what are my walls, right? So I want to be in the relative interior of top-dimensional cones. In order to achieve that, I have to sort of subdivide my fan sigma 1 such that the push forward of sigma 1 to sigma 2 is a well-defined fan, and then I just take the codimension 1 skeleton out. Yeah, you see a picture. I'm actually about to do an example. Okay. Right, but this was the missing ingredient. Now, after, you know, if we believe this lemma, I suggest that maybe if you have some doubts about it, make 2 such computations or so in the exercise sessions, then you'll believe it. And then we know that EV is a linear map. Another question, please.
Does it say on the third line from the bottom, VK0, K, mark N,
vk is 0 if k is a marked end. Yeah, so actually, let me do an example and answer the question again after the example, and then I hope that it will all make sense, okay? So I wanted to show you very precisely the effect of the evaluation map on the tiniest example that we can possibly think of. So we'll count lines in the plane through 2 points, okay? Yes, I know, that's just one. It's not the number that I care for, right? That's boring. But it's this, I want you to see the structure, the fans, the evaluation map, the effect of the evaluation map in this case. And to really draw the full picture, I have to pick an example as tiny as that. As soon as I make the example bigger, there's no chance to draw a reasonable picture. Yeah, so let's count tropical lines through 2 points. Tropical lines through 2 points. How would we do that? Now, after setting up this theory, I mean, before setting up the whole theory, what would you do? You would say, hey, okay, give me 2 points. I'm going to draw a line through it. That's your line. I'm done, right? Yeah, possible, it's legal, but it doesn't explain the theory behind it. And in order to give you a glimpse of what the theory is doing for you, let's do it more precisely. So what are we going to do? We're going to say, well, fine, our degree consists of 3 directions, -1, 0, 0, -1, and 1, 1, right? Those 3 directions here. That's our degree. Okay, furthermore, we're going to say we need 2 marked ends, because we need to meet 2 points. So we're going to say little n is 2. Number of elements in delta is 3. So our tropical moduli space, M0n trop of R2 delta, what is it? It's an R2 times M05 trop. Okay. Now, what is M05 trop? We want to use this distance map to embed M05 trop into R to the 5 choose 2 minus 5, right? So we can all use a moment to compute that. I think it's 5, right? It's too big. I can't seriously draw this fan. Too bad. But what can I do? It's a fan which is of dimension 2. It's a 2-dimensional fan in R to the 5. I can go and take the unit sphere in R to the 5 and intersect my 2-dimensional fan with the unit sphere. Yeah? What happens? All the rays of my 2-dimensional fan will produce points on the unit sphere, and all the 2-dimensional cones of my 2-dimensional fan will produce edges on the unit sphere. That means I'm just going to draw you a picture containing points and edges. And of course, since I don't have a unit sphere in R5 here, sorry, I only have a blackboard. So I'm going to draw my picture with vertices and edges as if it was a planar graph. But please remember, it's not a planar graph. So intersections of edges don't have anything to say. They just happen because I need to draw the picture somehow. Think of this as what you would see if you could honestly watch on a unit sphere in R5, okay? So how does this picture look like? It's a beautiful graph. It's the Peterson graph. It looks like this. So that's M05 trop. The times R2 I won't draw, right? Because that's just a linearity space. It doesn't tell me anything about the fan structure. You can forget about it. Okay, what do those rays mean? The rays correspond to those vectors Vi, I subset of 1 up to 5, and I, well, either 2 or 3, right? Because I need to have at least 2, and I need to leave out at least 2. But if it's either 2 or 3, I can as well agree that I'll only list those, right? Because it's symmetric. So I is 2. Okay, so I label all those rays with just 2 numbers. Something went wrong, sorry. That was still fine. Five, 1, 5, okay. 2, 5, okay. Now we're good, and now this is 2, 4 after all, okay. 2, 5, we don't need this. 1, 4, 2, 5, 1, 4, 1, 3, okay. Okay, good. So I had to pay a little attention here to make this consistent, because I want you, I mean, what are the two-dimensional rays now? The two-dimensional edges, the two-dimensional cones, yeah? The edges coming from two-dimensional cones, what are they? They are the orthons corresponding to the combinatorial types that have 2 rays, two bounded edges corresponding to the 2 rays, ray 1, 2 and ray 3, 4. I need to decide on the labeling here. Let's say this is 3, this is 4, and this is 5, okay? And the marked ends, yeah? So V1 is 0, and V2 is 0. And this is V3, yeah? V3 is this, V4 is this, and V5 is this. And I hope that this, coming back to the question, you asked the question before. I hope that this helps to answer the question. Great, okay. Okay. So let's actually not start with those cones because they are a bit ugly. Let's talk about, let's talk about this cone. What is this saying? This is saying that 3 and 4 come together and form a 3-valent vertex. And then the mark point 1 will be somewhere, right? Just contracted. It's just being contracted. Maybe I should draw it like this, yeah? 1, and then the second mark point will be there, and 2 is together with 5. Yeah, so I don't know, what do you prefer? Do you want me to draw points, or do you want me to draw like shadow edges that remind you that there was an end which is contracted? Which version do you prefer? Doesn't matter? Any opinions? Huh?
That one.
With the hair. Yeah, with the hair is always nice. I think so too. Okay, good. So, you think so too? Yes. Great. So let's continue. What is this cone? 1, 4, and 2, 5. So which one was 4? Lower, right? So 1 sits on 4. 2 sits on 5. And 3 is alone. 3 is in the middle. Okay. 1, 4. 1 sits on 4. And 3 and 5 come together. And so 2 must sit here in between. Okay, here we have 3 and 5 coming together. What am I doing? 3 and 5 coming together. And then 1, 2, now it's actually important to draw it with the hair. Because if 1 and 2 come together, they're all being contracted. And then there is another contracted edge in here. Yeah? So here's a question. You're kind of lost.
Can you explain the first one?
Yes. Okay, very good. So let's do this a bit more slowly. I didn't want to lose you here. Let's do this a bit more slowly, and then I hope it'll all make sense. 3, 4 is actually this guy. 3, 4, 2, 1, 5. And 2, 5 is, let me draw it like this now. 2, 5, 1, 3, 4, right? So who is in the middle? Who is on this edge? On the edge is going to be someone who has 2 bounded edges. And if I shrink one edge, I have this. And if I shrink the other edge, I have this. So it must be 1 who is in the middle. 1 is sort of jumping from here over there. Yeah? Okay, so this is how I understand, first of all, the tree structure of such an edge. Once I know about the tree structure, I try to draw already the image of this thing viewed as a tropical stable map. How do I do that? Well, I go and say, okay, 1 is a marked end, 2 is also a marked end. They are supposed to be contracted, yeah? So V is 0, contracted. 5 has direction 1, 1. 3 has direction -1, 0. This is 5. And this is 4. This has direction 0, -1. Yeah, and now you straighten this, and you see that picture. Got, yeah?
And just to confirm that, like, the directions are because you had chosen them before with the delta.
Yes. Yes, I need to fix the degree for all of this to make sense. The evaluation map needs a degree.
Thank you very much.
Yeah, sure. Okay. So this is a bit of a funny cone because the 2 points are going to be contracted to one and the same guy. Yeah, so evaluation map is highly non-injective here. Yeah, okay, doesn't matter. What's here is also 1, 2, but 1, 2 is sitting at 5 now. Okay. And finally here, 1, 2 is sitting at 3. Okay. Still have a bunch of cones to go, and I actually want to draw the pictures because I believe that it will be very interesting to see the full picture. Let's try that. Let's continue with this cone. 3, 5, 3 together with 5, 2 with 4. So 2 is here, 1 is here. Okay, this guy. 2 and 4, and 1 and 5. 2 and 4, and 1 and 5. Okay. This guy here. 1 and 5, and 3 and 4, so meaning 2 must be here. No? Okay. This guy here. 4, 5, and 2, 3. So 4, 5 come together. 2 sits at 3, 1 must sit in the middle. There's not enough space somehow, even though this blackboard is kind of big. So this goes here, okay? This goes here. Okay, so what is this guy? 4, 5, and 1, 3. So 1 sits on 3, 2 sits next to it. 1, 2, okay. Who are we missing? This we have, this we have, this we have. We are missing this. This we have, right? That's this, okay. We're missing this and this, right? So that's 2, 3, and 1, 5. 1 sits here, and 2 sits with 3. Okay. And then this guy. 1, 3, and 2. 4, 1 sits with 3, and 2 sits with 4. Now we're not missing many, only those 2, I think, so only 2 more pictures to go. Okay, so this is 1, 4, and 2, 3. So 1 sits at 4, and 2 sits at 3. And here 1 sits at 3, and 2 sits at 5. Now I believe we got all pictures. So what does the evaluation map do? The evaluation map sends this whole picture times R2, which I'm not drawing, but it's there, okay? Times R2, it sends it to R2 times R2. And this is evaluate the first point. And this is the second. Good, okay. But now this R2 and this R2 are the same, right? And the map restricted to that R2 is just the identity. So I can forget this part. And I can sort of focus on this, draw this picture of R2, and understand the image fan of my M05 here. Yeah? So let me do this. What is happening? Well, first let us look at the non-injective cones, at the cones where the EV map is doing something brutal, okay? So this ray is just being contracted to the 0 point, yeah? In this picture, yeah? So I view this as relatives, like a slice. So imagine here is where 1 is mapped to. This is h of x1 is EV1 of anybody. Okay. So this whole ray is just contracted. And all those two-dimensional cones along, they're all just mapped to that one red point over there, right? Because 2 is always mapped to precisely where 1 is. And if 1 is the middle point, 2 is also the middle point, and that's it. Okay. Other color. What other cones are there which are not going to be mapped to something two-dimensional? It's all those where 1 and 2 sit on the same ray. Do I have them all? No. Yeah. All those where 1 and 2 are being mapped to the same ray can't be mapped to something two-dimensional because 2 is always on the same line as 1. So where is this guy being mapped to? Maybe we should just label those. Number 1, green number 1. If 1 is that point, then 2 is going to be on the vertical upray somewhere. So number 1 is going to be mapped here. Good. Number 2. Now 2 is below 1, but still on the vertical ray, right? So number 2 is mapped here. Okay. This green guy, number 3. Now 2 is left of 1. Okay. 4. Now 2 is right of 1. And 5 and 6 finally. Here 2 is diagonally below 1. So this is 5. And for 6, 2 is diagonally up 1. So all those green two-dimensional cones get contracted to lines. Yeah? And this is actually the push forward. This is EV push forward of M05 drop times R2. This is the push forward fan. This is the fan structure I should impose here. And if I want to pick points in general position to count my tropical lines through those, I should pick them in the interior of those top dimensional cones. What are the top dimensional cones now? This is very pretty to see in this picture because you just see the cycle of 6 cones which is left. These are the 6 cones which are left and which are going to be mapped injectively, and they are going to be mapped like this, right? You see that? Yeah. So maybe we should do, maybe we don't want to do them all, but maybe like here 1 or 2 or so. The blue number 1 between 2, 3 and 1, 4 has to be mapped here between 1 and 3, right? Because we were always thinking, you know, what if point number 2 is somewhere here, and this is point number 1? Then we draw a line through those that looks precisely like the line that I sketched here for one, like, this is the picture corresponding here, sorry, like this picture that I've drawn for this edge, right? Okay. Yeah.
Could you repeat how you determined the first 6? Those first 6 edges you selected.
The green guys? Yeah, sure. Okay, so let's maybe focus on number 1 here shortly. So number 1 is the guy between 1, 4 and 3, 5. And are you happy with this picture that I've drawn? Okay, great. Now you imagine, you know, point number 1 is that point. So if I evaluate where the second point is for a curve that looks like this, where is it going to be? Somewhere here.
And you chose the 6 because they were adjacent to the red lines.
I chose those, yeah, you could view it like this, because the red lines are all going to be contracted to a point. And for that reason, those rays are also going to be contracted to a point. And for that reason, those two-dimensional cones have no chance of being mapped injectively one of their generators is smashed. They had to be mapped to something lower dimensional. Yeah, okay. Right, yeah, so this is the picture. This tells you how to pick points in general position if you want to draw a tropical line through them. And this also shows you that you have 6 different image cones in your image fan. So from that point of view, you have 6 different combinatorial types of tropical lines. They differ because of labeling now, right? Because here 1 is there and 2 is there. And here 1 is here and 2 is here. And so on, right? And the opposite cone is just reversed, yeah? Here 1 is there and 2 is there. Yeah? And this distinction happened just because I chose to label my points. And just just as a fun observation, if we pick points on this ray, yeah, a point on this ray corresponds to 2 points that are on a diagonal. So of course, this is not in general position. You could not draw a unique tropical line through those. There's a whole one-dimensional family of lines through those. So that's a reason to avoid those walls, yeah? There you don't have a well-defined finite count of tropical curves satisfying the point conditions. You should really be in the interior of your top dimensional cones, and then you see the right pictures. Any question left about this big picture? No, it's all fine? Yeah, here's a question. You want me to label those cones with blue? No?
If you just talk again through the one you already did.
Just talk again through the one I did? Yes, sure, okay. The one I did was this one, 1, 4, and 2, 3. And if I draw it as a map following this recipe, then this is the picture. 1 is on the lower guy, and 2 is on the left guy. Yeah, right. And my point 1 is now somewhere here, right? So 2 is somewhere in this cone. You could also make your life a little easier and just say, okay, this cone 1 is adjacent to the 2-dimensional cone green 1 and the 2-dimensional cone green 3, which are smashed to become rays. So it has to live between 1 and 3, right? Yeah. Okay, now? Any more questions about this picture? No, okay, good, but I hope you got an idea. So in general, you know, the fans are way too gigantic to draw them, but nevertheless, we got pretty close, I think, to getting a good idea of what is going on here. So, you know, we have this giant M0n trop living in a very big vector space as soon as n is sort of big enough to make the number interesting. We have the evaluation map sending to R2 to the right number of points. It's going to be a map of fans. As such, it has a well-defined degree. The degree is just, you know, a count of inverse images of a certain image point, which we can think of as a count of tropical curves satisfying my point conditions. And they have to be counted with a multiplicity. And for this multiplicity, we have several notions. The nicest is being, of course, the combinatorial recipe. Just take the product of triangle areas and you got it, right? Okay, so at this point, you may ask yourself, didn't she promise ages ago she would prove some nice recursive formula about those numbers? And now she spent almost 5 lectures talking about the numbers and how to honestly define them, right? Where's the recursive formula? Okay, the recursive formula will come now. I won't finish it in this lecture, there's no chance, 15 minutes are not sufficient. But it will be proved in the last lecture. But you will notice that what we did until here was not just to make our numbers sort of well-defined and view them as tropical intersection products in a tropical moduli space, but the 5 lectures we spent, they were also useful to develop the theory that you need to make this recursive formula also happen. So the proof will now, you know, use the same techniques that we established here. And yeah, I think it's an easy idea, at least. Maybe I shouldn't claim that the proof is easy, because there is still something. But it's a beautiful idea. I hope you will like it. So yeah, let me just erase all the blackboards to produce some space. that we sort of start fresh into the last topic, so to say, for this lecture series, which is finally the Kontsevich formula. Okay. What I need to introduce in order to talk about the Kontsevich formula are forgetful maps. We have the forgetful map, forgetting end j from m0 entrop to m0 n minus 1 trop, and it just forgets the end j. It's really hard to move here. Forgets the marked end j. It is possible that then it has to straighten edges somehow. So let me just, not define anything formally, just draw a picture. Assume the marked end j is right next to some other end I. Yeah. Well, sorry, I shouldn't draw those dash now. Marked ends doesn't have a meaning right now. We're just in M0 entrop. Yeah. Okay, assume it looks like this. Then what does it do? It just forgets j. Yeah, just take it away. Then there's just the end I. That's it. Okay, what if the end j, which I mean to forget, is somewhere, and it looks like this? I want to just forget it. If I do that, I produce a two-valent vertex. I don't like two-valent vertices. I want to be stable. So I straighten this two-valent vertex and just treat it as one edge, which then has to be of length the sum of those two, L1 plus L2. So this is how I forget ends in terms of, the tree pictures. In coordinates, we're just project all coordinates of the form jk away for some k. Yeah, because the distance to j doesn't play any role anymore. J has gone. Yeah. So in our distance coordinates, which are of the form some n1, n2, nk, nj, just throw those away that have j. It's just a projection. It is linear. That's nice. Okay. Now you can imagine easily that I cannot only forget one end, I can forget multiple ends, right? And in this Kontsevich formula proof, it will be important to forget all ends but 4. Yeah, so I have a map to M04, to tropical M04. Let me just again draw an example for you. So here's some tropical stable map, which has some contracted ends here, here. Here's another one. Here's another one. 3 and 4. And as usual, I'm drawing my tropical stable maps with the image already. Yeah, I'm putting them into the plane. Yeah. Okay, and now what happens is I forget everybody but 1, 2, 3, 4. I need to keep this subgraph. Okay. And then the length between 1, 2, so first of all, we observe that in my curve, 1 and 2 and 3 and 4 are going to be separated. Yes?
Use a different color to mark over. I cannot distinguish the two.
Oh, sorry. Is it going to be any better if I draw yet again? I try to draw next to it. Yeah? Does that make sense?
Yes, thank you very much.
Yeah, like this. Okay, great. Yeah, so the image of this curve in M04, the image of this stable map, this tropical stable map in M04 trop, this is ft. So this is some gamma with xi's and h, right? And this is ft of gamma xih. And this is this. And this edge has length. This is L1, this is L2, L3, L4. It's the sum from L1 up to L4. And it has 1, 2 here, and 3 and 4 here. Yeah? So this is how I forget everything but 4. So now I'll do something which at first glance seems weird, but it will make sense. So I'd like to ask you to be a bit patient with me here, because just as we move on, okay, I can't explain it today. So it's a cliffhanger for next class, okay? I will tell you why this is happening next time. So we pick n equal to 3D now. Remember, it used to be 3D minus 1 for counting curves through 3D minus 1 point. We're taking an extra point for some reason. We do that. Let's just check what the dimension then is of my M0n trop of R2, and let me write D, where D stands for, D edges in the 3 special directions, right? What is that? The dimension is n plus 3D minus 1, and that is 6D minus 1. Okay. Now I'm going to define a fantastic map, which is called pi. And what it does, it evaluates the x-coordinate of h of x1. Then it evaluates the y-coordinate of h of x2. Then it evaluates both coordinates for the remaining points. And then it forgets everything but the 4 marked points. So this map goes from M0n trop R to D to R times R2 times and so on times R2 times M04 trop. So that's a bit sad, but let me try to do it like this. So how many copies of R2 are there from point N to point 3? So these are 3D minus 2 such copies. So in terms of dimension, 2 times 3D minus 2 plus 1 plus 1 plus 1. And that should be hopefully equal to 6D minus 1. Works. Great. Yeah, so we have a map, which is just a linear map, because it's composed of linear maps, from one balanced fan to another balanced fan of the same dimension, which is irreducible. This is irreducible, of course. Just a tropical line times some linearity space. It's irreducible. Great, okay. So what we can learn already is that this map fits into our context. We know that the degree of this map is constant from the big theorem we just proved at the beginning of this class, right? Okay, let me say a few more words about what this map is doing. Trying to put this into this picture, but it's not so easy. So I want to evaluate the x-coordinate of h of x1. So don't care about the y-coordinate. The y-coordinate can be anywhere, but the x-coordinate should be on this green line, okay? And then I evaluate the y-coordinate of the second mark point. So that point should sit on this green line. And then for the remaining guys, 3, 4, 5, and 6, I fix points. And I want the curve to pass through these points. Now, if you look at this picture, you see meeting a line is not really a condition, right? I could sort of move this curve, pull this vertex a little bit upwards, adjust my length here, and then I would still have a curve that meets the line, right? But what is happening if I move this curve upwards is, of course, I change this length here, the length in the image of the forgetful map. Yeah? So this picture that I've drawn is actually an inverse image of a choice in here, which is the first green line, second green line, the green points, this red picture. This curve that I've drawn is a pre-image under pi in here. Okay, just so that you see a concrete example of such a pre-image. And D is 2 here, of course, right now. And N, accordingly, is 6. So that works. Okay. Right, just to give you a quick outline of what is going to happen. So we built this crazy map pi. We don't know why at the moment. We just did it. We know it's a map of fans. It's constant. The degree is constant. That's perfect. What we're going to do in the next class is, since the degree is constant, we can pick 2 points that we really like. By points, I mean, collection of line, point, element in M04 drop, right? We can pick 2 such guys that we like and count inverse images. And that will be equal for our choice, for one choice and for the other choice. And that will produce an equation for us. And this equation will become the Kontsevich recursion. We just sort of have to identify all the terms in the equation and somehow relate them to curves passing through points. And one way to do that is by saying, hey, there might be curves who meet sort of the crossing of those 2 lines, right? And this is like an additional point condition, and that will be a summand of ND showing up in our equation. And then we'll have contributions where we say, which end up being reducible curves that satisfy the point conditions. Okay, and there are lots of details that still have to be spelled out. We'll do that next time. Okay.